Okay. So today we are looking at concealed quadratics. And when they say something is concealed, it means that thing is hidden. So in this particular case, we are looking at quadratics that are somehow hidden in the form of logarithms, in the form of exponents, or in the form of surds. Let's start with an example. You have, for example, this equation, e to the power 2x minus 3e to the power x plus 2 is equal to 0. This is an example of a concealed quadratic. And with concealed quadratic, we can always let what we can see. For example, this is e to the power x here. If you look at this e to the power 2x, is the same as e to the power x times e to the power x. Because when you use the first law of logarithms, that gives us e to the power 2x. So we can make e to the power x to be equal to t. So we can say let e to the power x be equal to t. And we can break down or simplify this quadratic. Instead of using e to the power x, we will use t. So in this case, this will give us, here we'll have t squared minus 3t's, right? So I can solve by factorization. So minus 1t minus 2t's plus 2 equals 0. I want to solve by factorization. Okay, we now group just like we did previously. We now group each, we pair them in twos. Or from here, you can use your quadratic formula to solve directly. But I love to solve using factorization. I love factorization so much. And when we group these two, the highest common factor here will be t. We factor it out. With this other pair, note that this the sign that is in between, that separates these two, is left outside. We now factor these two out. The highest common factor here is 2. We bring it out.
Factor out 2.
We are left with. All right, here I am still having x. Here it's supposed to be t.
T plus t minus 1.
Yes, sorry about this. This is actually t. It's typo. Yes, because when they don't type, it is not clearly seen. So I'm sorry about that. This is
t plus 1.
T minus 1.
All right, now let us look at this. Now look at this. Minus 2t's, right? Divided by minus 2. It gives us plus t, right?
Yes, sir.
Then if we take now this plus 2 here, plus 2 divided by minus 2 gives us minus 1.
Yes, sir.
So don't consider these brackets that are here. These brackets that are here, please don't look at them. I was just showing how we can group them. Normally, I was supposed to underline because it can be a bit misleading. Thank you so much. So we now see that these two brackets are the same. Let me just correct this before I come back. Who is sitting with a baby? All right, let me bring this here. This will give us so here we have a t, not x. All right, it's clear now. So we have, since these two brackets are now the same, we can now bring them together. We copy out one of the brackets. Then we have t minus 1 into t minus 2. What is left outside? This is equal to 0. And when we solve for t here, we have t equals 1 or t equals 2. But we equally know that we were not actually solving that for this t. We had said that let t be equal to e to the power x, right?
Yes, sir.
So e to the power x is equal to 1, or e to the power x is equal to 2. Now, this first one, we can solve using indices as we solved in the first lessons in chapter 1. And we know that 1 is the same as e to the power 0. Replace this one with e to the power 0. And we have e to the power x. This now becomes e to the power x is equal to e to the power 0. And now that the bases are the same, we have made the bases the same, the powers will equally be the same. So our x is equal to 0. For this other one, it is not possible for us to make the bases to be the same. So what we are going to do there is, we are going to take ln on both sides. Remember, ln is log when the base is e. All right, I'm
Yes,
trying to
sir.
read the person that is the child. Rodrigue, is your child studying?
No, sir. No, sir.
Who has the child?
Sorry, sir. I'm the one. But
All right. So here, since we cannot make the bases the same, we will take ln. Why are we taking ln? It's best to take ln because the base here is e, and ln means here the base e. So when we take ln on both sides, we will have ln e to the power x is equal to ln 2. Ln e to the power x equals ln 2. But we know that ln e to the power x can be written as x ln e from the laws of logarithms. And finally, we equally know that ln e is 1. Why? Because the base for ln e or for ln is e. So we have a base to the same number, and this will just be equal to 1. So this will give us x to be equal to ln 2, and these are the roots of this concealed quadratic. Please look at it again very well, and if you have any questions, you can ask. You can equally use the discriminant from this step. Our delta, we look for b squared, that is b squared minus 4ac, and we solve this quadratic formula to the same results. Any questions, class?
No questions, sir.
All right, let the others look. Any questions from anybody?
No, sir.
Right. And let's
Sorry.
take another. Yes.
the Ellen, wait, how? Sorry, I was a little bit distracted. So
Yes. The ln here.
yeah.
Now, if you look at this one, look at e to the power x equals 2. Can you see this?
Yes, sir.
Now, we want to look for a way such that we can make the bases the same here. But you know that you cannot express, you cannot make 2 to turn into e. There is no way. So with this type of problems, exponential equations, we cannot solve them using indices because we can never make the bases the same. Unlike this one, we know that 1 is the same as e to the power 0. But here, we cannot write 2 as e to the power something. So with this type of equations, we solve them using logarithm. Are we together?
Yes, sir.
Yes, so we can take log on both sides. That is okay. But here we can use a shortcut because our base here is e. Can you see it's e to the power x? It will be better for us to use log base e. Linear means log base e. Whenever you see ln, it means that it is log base e. So we are taking log base e on both sides. Are we clear now?
Yes, sir.
Yes, so whenever we are to use logarithms and the base is e, we can just write as ln. Ln means the log of the natural number e. So the base here is e, though you are not seeing the e, it is log base e, which is ln. When we take ln on both sides, this is what we have. But log base e of e to the power x is just the same as x log e base e. And when you have a log of a number to the same base, then that becomes 1. So ln e is equal to 1. If you look at the previous notes and lessons on logarithms, you see all of this. We have really answered so many questions on these equations. So from here, since this number here is equal to 1, x times 1 is x, and x is equal to ln 2. And you can further simplify. Ln 2 is 0.693 on calculator. Any other questions?
No, sir.
All right. If there are questions next week, since next week will just be tutorials, and we are begging on you, look at the past questions, maybe from 2010 to 2021, and remove all the questions that involve what we have already answered in these topics, so that we can compile them, and that will be our tutorial. Some of them will even come in the quiz, which, as we said, all students working with us are required to take the quiz, so that we know which place is lagging, so that we can strengthen it, and we know exactly what the students have understood. Let's take another example. Now we have this other concealed quadratic. We have this concealed quadratic here. Oh, let me clear everything. With this concealed quadratic, we have log x base 3 plus 2 log 3 base x minus 3 is equal to 0. So this is another example of a concealed quadratic, though you are not seeing any square anywhere. And if I copy back this one, you have an equation of the form log x base 3 plus 2 log 3 base x minus 3 equals 0. Now, look at this log 3 base x and log x base 3. Are the bases the same?
No, sir.
It means that we have to do something to make the bases the same. Otherwise, it will not be possible for us to solve this quadratic equation, which is concealed. So what we do here is that we know that the bases are not the same. And the only thing we can do is a change of base. We do a change of base. I would like all the bases to be base 3. So we will be doing the change of base at this expression, or at this point here, log 3 base x. So with the change of base, we will have log x base 3 plus 2 log, now see how we have changed the base here. This is my focus. So to change the base here, the numerator will be this number, this 3. And the denominator will be this x. And you see, this is the 3 here. At the denominator, we have x. And I say, I want my new base to be 3. I now take 3 for the numerator as the base and 3 for the denominator as the base, so that it will correspond or coincide with this other base here, which is 3. Class, are we together?
Yes, sir.
So for the change of base, this one here becomes the numerator, and this x becomes the denominator. And then we have our new base. Our new base, we have decided that it should be 3, so we can have a common thing all through. But we equally know that log 3 base 3 is equal to 1, right?
Yes, sir.
Yes, sir.
Log of the number to the same base. So this will now give us log x base 3 plus 2 into 1 over log x base 3 minus 3 equals 0. At this point, you can now multiply all through by log x base 3. When you multiply each of the terms by log x base 3, we'll have log x base 3 all squared, that is this one now times this one, this time this, the same thing squared, plus 2. It will now cancel out here, we'll be left just with 2. Now minus 3 into log x base 3 is equal to 0. Can we now say that we have a quadratic?
Yes, sir.
We have a quadratic in which we can say let this log x base 3 be equal to a t or any other number that is not already appearing here. So we can say let log x base 3 be equal to y. Let me use y now. And here we'll have y squared plus 2 minus 3y equals 0. We can now write it in the general form as y squared minus 3y plus 2 equals 0. And when we solve for y, we'll have y equals 2 or y equals 1. This one is the same like the previous quadratic that we just saw. The roots are the same as that one. So that's why I did not bother to solve again. But at this point, we know that we had said let our y be equal to log x base 3. So this therefore means that log x base 3 is equal to this first root, or log y, or log x base 3 is equal to 1. So with this, to solve this one, since we have log, I can convert to exponential form. To convert to exponential form, you will have this base here. So this power is equal to this number. So this x should equal to this base raised to this power. The power is always on the right hand side. So here our x is equal to 3 to the power 2, and 3 to the power 2 is equal to 9. Similarly, log x base 3 is equal to this other root, which is 1. And at this point, x will be equal to this base raised to this power, 3 to the power 1. And that will give us x equal to 3 to the power 1, which is 3. So that is what we have. All right, let me go back. Please, any questions at this point?
Not really.
All right. We equally have some sort of concealed quadratics in certs. We will see that in the tutorials. And as I've said, please look at the questions from 2010 to 2021, because that is what is going to comprise our tutorials and part of the quiz with some other questions. All right, no questions. Can we go to the next part?
Yes, sir.
The next part will be looking at nature of roots. In the last class, we tried to crash nature of roots a bit, and I got complaints that we were a bit fast. And so we'll look at it again today, and I think that you understand them better. So nature of roots. I'll start by taking this example. This is one past question, which I just took. We have given that this quadratic k plus 5x squared minus 10x plus 2kx equals 9k is a quadratic equation. Find the values of the constant k for which the roots are equal. What is the condition for the roots of a quadratic equation to be equal?
A small constitutional population in need of any kind of reassurance.
What is the condition for the roots of a quadratic equation to be equal?
B plus 4AC must be equal
To 0.
greater than or equal to 0.
All right, so for the roots of a quadratic equation to be equal to 0, thank you so much, the discriminant must be equal to 0. Are we together?
Yes, sir.
So the discriminant must be equal to 0. Anyway, the first thing we'll do here is to arrange this equation in the general form. As you can see, we are supposed to be having 0 on the right-hand side, but you have a k there. And this k, or this 9k, is a constant term. So we'll bring it to the left-hand side. And this is the condition that you have just given. So it is equal to, when you hear about equal, you use equal to 0. When the roots are equal, you use discriminant should be equal to 0. But if they say that it should be real, we use greater than or equal to 0. If they say they should be distinct, we use greater than 0. So now let's arrange this equation in general form. We have to bring this one to the left-hand side. We note that this term and this term are terms in x, so we can group them. This one is a constant term because it does not contain x. So this will give us k plus 5x squared plus x, we factor out this x, plus x into minus 10 plus 2k's. Then bringing this one to the left-hand side gives us minus 9k's equals 0. So this quadratic is now in the form ax squared plus bx plus c equals 0. Normally, I should put this one before the x because this is my b, but it's okay. So the next thing now, following this condition that the discriminant should be equal to 0, because they say that they want the roots to be equal. For the roots to be equal, the discriminant should be equal to 0. So these are b squared, this term squared, minus 4 times a, our a is k plus 5, times c, as c is minus 9k, should be equal to 0. At this point, you can expand and simplify. Expanding this one, you have 100 minus 10 times 2k's minus 20k's minus 20k's, that equals 2 times. Then plus 2k squared gives us 4k squared.
Okay.
Yes, minus 4
Square.
times k is
Minus 4.
4k.
Minus
All right, and then minus 20. In fact, when you expand all through, this is what you obtain. So minus 4 times k is minus 4k times minus 9k is plus 36k squared. Minus 4 times plus 5 is minus 20 times minus 9k is plus 180k. We now bring together the terms in k squared. This will give us 4k squared plus 36k squared is 40k squared. And the terms in k, we have plus 180k minus 40k. That is plus 140k. Then plus 100, which is the constant, is equal to 0. You can still divide all through by 10 or 20, and a quadratic will look like this when you divide all through by 20, because 20 is common. 2k squared plus 7k plus 5 equals 0. At this point, you can solve this quadratic as well. And when we solve this quadratic by factorization or any other method, the values of k will be k equals 1 or k equals 5 on 2. sorry, minus 5 on 2.
Um,
Yes. Yes, please. Any question? All right, let's look at it a bit before we have, if you have any questions, you can ask. Any questions?
Things that have afterward evidence that collected since to show that Facebook's purchase of WhatsApp and Instagram.
No, sir.
All right, no question. So we can move ahead. Let's look at another example that resembles this one. So we have find the value of the constant k for which this quadratic equation has imaginary roots. Has imaginary roots. What is the condition for imaginary roots?
it must be.
So that means
It
the
must be less than
discriminant is
zero.
negative.
Okay, the discriminant must be negative, or the discriminant must be less than 0. So our b squared minus 4ac should be strictly less than 0. So this is it here. It means z should be strictly less than 0. So at this point, we have our b squared. This is b, 2 minus k squared, because this one is already in general form, minus 4 times a, our a is 2, times our c is 2 into 2 minus k's. This should be strictly less than 0. We expand. And in expanding and solving, it may make it longer. A shorter way is to observe that 2 minus k is common. And you can still expand and factorize and all of that and simplify, no problem. But we observe that 2 minus k is common. You can see here. So I can just factor this thing out. So if I factor this out, this one is one term, and this another term. So we factor 2 out, 2 minus k. We have 2 minus k into, here we'll be left with 2 minus k. All right, let me write it, expand it and write it in a way that is clear. So now it is now clear, 2 minus k squared. It's like this. So when we factor out one of these, we'll have 2 minus k. What is left in the bigger bracket now is this 2 minus k minus 4 into 2 into 2. So we'll be left with 2 minus k minus 4 into 2 into 2. And that gives us minus 16. That will be strictly less than 0. So at the next step, we'll have 2 minus k into minus 14 minus k should be strictly less than 0. So factorization is shorter for this one. Now, there is something you have to observe here. This one is not an equation. It is an inequality. So we don't solve it directly as we solve equations. Our solution will be a range of values. So we first of all start by looking at the boundary solutions. Boundary solutions means equate each bracket to 0 and solve for k. So when we equate this to 0 and solve for k, our k is equal to 2. And here, our k is minus 14. Those values are called the boundary solutions. Now we can proceed by testing. We place our boundary solutions on the number line. And the solution is either going to be k is strictly less than negative 14, or k should lie between negative 14 and 2, or k should be strictly greater than 2. So we can test. Let us test. We take any number below minus 14 and test in this equation here. We take, for example, minus 15 now.
Yes, sir.
Yes.
Substitute.
We can.
Substitute now.
Yes. Okay, yes. And then we substitute in this. Thank you. So we take minus 15 and substitute here, or even minus 16. In fact, any number less than this minus 14. So we'll have 2 minus 15. This one is positive, right?
Yes, sir.
Yes, sir.
Then we now take minus 14 minus 15. This one is also positive.
Yes.
So positive times positive is positive. And a positive number is never less than 0. So it therefore means that this first region does not satisfy. This region below does not satisfy. So we can test, let us test now another region that was the positive part. So this region does not satisfy. Now let's take a number between minus 14 and plus 2. We can take 0, for example. Now 0, go faster.
3. 1.
Zero.
1.
All right. Let's just
Zero.
say 0 is faster, right? You can take 1, you can take any number in between, but I think 0 will be faster. So if you put 0 here,
Yes, sir.
2 minus 0 is 2, which is positive, and minus 14 minus 0 is negative. So we have positive times negative in this case is going to be negative. So this region satisfies. Now let's test any number above 2. For example, above 3. 2 minus 3 is negative. 2 minus 3. Minus 14 minus 3 is also negative. Negative times negative is positive. So the region above 2 does not also satisfy. So the only one that satisfies is from minus 14 to plus 2. So our solution set is K is greater than or equal to negative 14, less than or equal to plus 2. So that's the solution set for this given question.
Yes. I do not understand the first how you started. So,
You don't understand here?
yes, sir.
All right. Now let me start at this point, from this point. At this point, we have an inequality.
No, sir.
Yes.
I'm the solving.
The solving from where?
From the starting.
Okay, from the starting.
Yes, sir.
All right, let me just take it again. Now, from the starting, this is what happens. From this question, find the value of the constant k for which this quadratic has imaginary roots. Now, for a quadratic to have imaginary roots, there are some conditions it must fulfill. And the condition that a quadratic should have imaginary roots is this. All right, let me look for one thing and show. Okay, we're left with just 10 minutes. Let me look for something and show you which is going to be clear. Somebody just joining now. All right, welcome, Victory. Why did you are joining the class so late? All right, now the condition is that for a quadratic to have the discriminant, this is a discriminant, right? This discriminant should be strictly less than 0. This is the condition for a quadratic to have imaginary roots. But this delta is b squared minus 4 a. Please, just a minute. Yes, please. Yes, good morning. We are fine. Yes, I'm in class now. Can we talk later?
Yeah, we can talk later.
Yes. So this is the condition for a quadratic to have imaginary roots. Are we there? Are we together?
Yes, sir.
Yes. So this is the condition. So we now come to this quadratic here, and we apply this condition. This is the quadratic ax squared plus bx plus c equals 0. So in applying this condition, we will have a b squared. This is b, right? We square it
Yes, sir.
minus 4 times this a, which is 2, times c, which is this. Do you now understand where we are coming from?
Yes, yes, sir.
Good. So when we simplify at the end, this is what we have. And since it's an inequality, and following what we did from the first chapter, this is how we solve inequalities. We have to test which region satisfies. Because with the inequality, we have 3 regions here. The region below minus 14, the region between minus 14 and 2, and the region above 2. So we have to test each of the region and see which one will satisfy this inequality that we have here. And after testing, we see that the region is from this minus 14 to plus 2. Are we now together? Are we together? Are we together? All right, so let's take another example. Oh, I think I took the second example before the first. I'll have to go back. Clean the board. Yeah.
So let's do that first one.
All right. I'm struggling to get to the page.
Given that the roots of the equation x squared minus x plus 2 equal to 0 are alpha and beta, find a quadratic equation whose roots are 1 over 1 plus alpha square and 1 over 1 plus beta square.
All right, we are searching. Are we there?
This is it.
All right,
Yeah,
thank
this
you.
is it.
Okay. So this is another example. This is the first one I wanted to do actually. Given that the roots of this equation are x squared minus x plus 2 equals 0 are alpha and beta, or given that the roots are alpha and beta, find now a new equation whose roots, not roots, are 1 over 1 plus alpha squared and 1 over 1 plus beta squared. So the general form for a quadratic equation, that is for the sum product property form, is x squared minus sum of root x plus product. So this is identical to this. At this point, as I said before, you must always make sure that the coefficient of x squared is 1 before you put this identical, you see that it's equal to this one, or before you say that it's identical to this other one. So at this point, x squared is identical to x squared, and minus x is identical to minus into alpha plus beta x. At this point, you can see that alpha plus beta is equal to 1, right?
Yes, sir.
Yes, sir.
Alpha plus beta is equal to 1. And when we equate this to this, we see that alpha beta is equal to 2. So these are sum and these are products. Now, for us to form the new equation, we need the new sum and the new product. So what is a new sum? We take what has been given in the equation, or in the equation rather. A new sum will be this plus this. So that will be equal to 1 over 1 plus alpha squared plus 1 over 1 plus beta squared. Our LCM here is the product of these denominators. So LCM is 1 plus alpha squared into 1 plus beta squared. I'll not simplify, I'll leave it like that for now. So this denominator divided by this, 1 plus alpha squared will be 1 plus beta squared. Then this denominator divided by 1 plus beta squared will be 1 plus alpha squared. You can bring like terms together. That will give us 2 plus alpha squared plus beta squared. We have seen this one before. We can replace alpha squared plus beta squared by alpha plus beta all squared minus 2 alpha beta, right? All right, so let's expand the numerator and denominator. When we expand the denominator, this is what we equally see. Now, we can replace this the same quantity here, this alpha plus beta all squared by alpha plus beta all squared minus 2 alpha beta, which we just saw in the previous example. So this will be equal to 2 plus alpha plus beta all squared minus 2 alpha beta. So I've replaced all of this quantity by this. Alpha plus beta all squared minus 2 alpha beta. That is what we do for the sum of squares. For the denominator, I'll do the same thing. I'll have 1 plus alpha plus beta squared minus 2 alpha beta. Can you instead of use this other uppercase bracket? So this alpha plus beta squared has now become alpha plus beta all squared minus 2 alpha beta. Then we continue with this term outside. But we already know that alpha plus beta is 1 and alpha beta is 2. So we can replace all those values here by what we already have. So this will give us 2 plus 1 squared minus 2 into alpha beta, which is, that is 2 times 2. All that on, we have 1 plus, this is 1 squared minus 2 into 2. Somebody's putting on the camera. Then plus 2 squared, and this gives us, when we simplify all of this expression, it gives us minus a half. So our new sum is minus a half. Now we need a new product too. Our new product will be the product of this and this. So when we open out these brackets, we'll have This denominator will just be the same thing that we have here now because it has not changed. This is it here. So just copy out this one. These are the values that we have here. So this will just give us 1 over 1 into alpha plus beta all squared minus 2 alpha beta plus alpha plus beta squared. And when you simplify, it's going to give us a half. These are the same values here. It's going to give us a half. So what's our new equation now? A new equation will be x squared minus the sum of roots. The sum of roots here is minus a half. So minus a half x plus the product plus a half equals 0. We can multiply all through by 2. And this is what you have finally. All right, let's look at it and see if there are any questions. Any questions? Victory, are you getting me?
So is that minus? Why is it? Okay, it's positive. It's okay, I've seen it.
Yes, when the two are together, not separated by anything, is positive. Thank you. Is that Victory?
No, it's Junior.
Please, is Victory getting me? Is Victory there?
She's trying to talk.
Let her put on her mic. Her mic is on, and why is her voice not coming out? All right, we try to see what you can do about that. Her mic is actually on, but the voice is not coming out. I don't know why.
So we have a half x plus a half.
So the screen has disappeared.
The screen has disappeared.
Yes, sir.
No, sir.
The screen is visible.
The person should check the screen. The person whose screen has disappeared, the person should check again.
So please explain the new equation again.
All right, the new equation. Okay, the new equation is given by, you say x squared. This is
Yes,
what you have
sir.
here, right? Look at what you have here. See, I'm copying this one.
Yes,
I'm
sir.
using this one. Yes, you have x squared minus the sum. A new sum. You are using the new sum. A new sum is minus a half. So we have x squared minus. That sum is minus a half. So that's why we have two minuses here. Minus
sir.
a half, and then we copy x. Then plus product. A new product is a half. So that's why we have it like this, plus a half. These two combinedly give us plus. So we have x squared plus a half x plus a half. And when you multiply all through by 2, this is what we have. Is it clear now?
Yes, sir.
Are there any other questions, guys?
No, sir.
All right, let us look at the past lessons that we have already worked on. And let me just show some 1 or 2 things. Don't know if I'm going to see the screen. Okay, trying to look for, don't know. Okay, this one. Okay, let me just put on something so that you can actually get to it. I hope people can still get me.
Yes, sir.
Yes, sir.
All right, let me share this other one that is about to open. It's taking some time. The connection is not very good today. Okay, it's opening. Okay, at the block, the notes and the past classes are there. They're all there. So if you just come to this block, you actually get exactly what you are searching for. This is our block where you have the notes. And for this week, these are the lessons we have already covered. We have already covered absolute value equations. And the notes are there equally. We have equally covered absolute value inequalities. We have already looked at absolute value inequalities. We have looked at surds, roots, and simplification. We have looked at indices, the laws of indices and equations involving indices, as well as logarithms. The notes of logarithms are there, but the quiz is not yet there. And normally, this is June 2021, paper 1. I think you can equally look at it. It's already is available online. And we are here in chapter 2, where we have the theory of quadratics. And in this theory of quadratics, we have covered factorization, concealed quotes, completing the square, and the quadratic formula, nature of roots, forming a new equation with roots. And you can find all of this. I think you equally have a bit of material on further maths. Yes, on further maths, there's a bit of material on that. We have beginning with matrices. I think the further maths is slower. Then for the past questions, you can always get to. Are you seeing my screen?
Yes, sir.
Yes, sir.
Yes, so the past questions you can always get to you type www.gcemathspanel.blogspot.com and you take you to the page where we have past questions, GCE past questions. And at that point, you can actually select the ones that you want. So here we have online classes. If you click here on online classes, it takes you to this class, to this page where we are right now. And then the technical section too, we have technical papers there. Here we have A-level papers. If you click here, it takes you to the A-level papers, www.gcemathspanel.blogspot.com. And these are the past papers for the past years. You have to go down a bit before you start seeing the papers. So this is 2020. We have not yet put 2021. If you click on any paper, the paper will open automatically. You are doing statistics, for example, the person that is doing statistics there. If you click on statistics, it opens automatically. One click. You don't have to sign in or any password or anything. The paper just opens and you can decide to download, or you can just work with it directly as it is there. We will focus on forming a quadratic equation from another equation whose roots have been given. The first thing you have to understand is that any quadratic can be written in the form x squared minus sum of roots plus product equals 0. So for example, this quadratic can be written as x squared minus, we have squared, that is, we first of all divide all through by these two, such that the coefficient of x squared here is 1. We have 1x squared. Then, in this form, what we have here is the sum of roots. And this other term is the product of roots. In fact, whenever a quadratic is in the form x squared without the a, or in the form x squared where the coefficient of x squared is 1, then it is in the form x squared minus sum of roots x plus product of roots. So if you look at this quadratic at the beginning here in this form, it is not in that form which I've just mentioned. So it therefore means like what you have here, let me annotate. We have, let me take this down. Look at this equation. This one is not in the form of x squared minus sum of roots plus product. And why is that? It is because the coefficient of x squared here is not equal to 1. So for me to put it in that form, the first thing I have to do is to divide all through by this coefficient of x squared here, which is 2. And when we do that division, we will be left with x squared minus sum of roots plus product equals 0. And this second step is in that general form. Now, from here, since the general form is x squared minus sum of roots plus product, it therefore means that minus a half x is equal to or identical to minus the sum of roots x. And this plus 3 here is equal to the product of roots. This equation tells us that the roots of this equation are alpha and beta. So first we have to look for alpha plus beta and alpha beta before we look at the second part of the equation. So our first thing to do here is to look for alpha plus beta and to look for alpha times beta or alpha beta. So at this point, we see that our alpha plus beta is equal to a half. Can everybody see that?
Yes, sir.
Because we have minus a half x is
a
the
half,
same as minus into alpha plus beta. It therefore means that this a half is alpha plus beta. Are we clear?
Yes, sir.
Okay.
Yes, and then this alpha beta, because it's plus 3 is equal to plus alpha beta is equal to 3. So alpha beta is equal to 3. At this point, we can now look at the second part of the equation. This second part of the equation is telling us that we should form a new equation whose roots are alpha minus 2 beta and beta minus 2 alpha. What do we require to form an equation? What we require to form an equation is the sum of roots and the product of roots. For example, if you tell me that the sum of roots for an equation is a half and the product of roots is 3, and I should form an equation with those roots, this is what I will do. I'll just say x squared minus that sum of root, that is minus a half x, plus the product of roots 3 is equal to 0, and form an equation. Now, they want us to use these values that we already have to form a new equation. So what I'll need here is a new sum. And that new sum will be what we have here, alpha minus 2 beta plus beta minus 2 alpha. That will be my new sum, because I'm using the equation. Alpha minus 2 beta plus beta minus 2 alpha. I can see that if I simplify this, I will have alpha plus beta, if I open out the bracket, or alpha minus 2 alpha is minus alpha. Then minus 2 beta plus beta is minus beta. So this will be the result. When you open out the bracket and simplify, our new sum will be minus alpha minus beta. It almost looks like this one now. So what I'll have to do here is to put bracket, I'll factor out this negative one, and I now have minus into alpha plus beta. Then my alpha plus beta is equal to a half, because I have to use what I've been given in this first part of the equation to continue. That is why I was looking for alpha plus beta and alpha beta, so that I will use in the new sum and in the new product. So my minus into alpha plus beta will be equal to minus a half, because alpha plus beta is a half. So our new sum is minus a half. The next thing we need is a new product, because we need a sum and a product to form a new equation. So my new product will be this alpha minus 2 beta, that's in brackets, times this beta minus 2 alpha in brackets. So this will give us alpha minus 2 beta times